This is the 12th installment of Advanced J1939. In this edition, we're going to take a look a little more detail about the acknowledge bit and the amplitude of the acknowledge bit. So a little bit of review looking at some real CAN traffic where I have several controllers on the CAN bus. We can see that this particular controller, when it's transmitting, the CAN high voltage with respect to ground is about 3.7 volts. The CAN low voltage drops to, for the dominant bit, down to about 1.276. However, when the acknowledge bit is transmitted by all of the other controllers, we can see in this case that we have a CAN high voltage of, let's see here, we have a CAN high voltage of about 4.154 and a CAN low voltage which drops down to less than 1 volt, about 0.9 volts. So we can see there's definitely in this messages, if we look at these packets, we can see the same kind of phenomena occurring. We'll talk a little bit about why that is occurring for us. So if I look at this, we can see it by the difference in voltage, the math, the A minus B, we see the same thing. So I'm sitting at a difference of 2.51 volts between CAN high and CAN low. And during the acknowledge bit, this is increased to about 3.25. If we look at this message, the last bit of the cyclic redundancy check just happens to be a 0. We then have this delimiter period. This delimiter period is 1 bit in width. So for our 500K CAN bus, this is 2 microseconds, 2 millionths of a second. If I then look at the acknowledge bit, we can see that it is also 2 microseconds approximately in width, and then we have the other delimiter, and then we have the end of frame. So if you recall from the last episode, if all of the controllers or whichever controllers have received the message correctly and calculate the CRC the same as was transmitted by the transmitting controller, this bit acknowledges that I've got the message and I've interpreted it correctly. This occurs regardless of whether the controller cares about that message or not. If the controller is on the CAN bus, it's supposed to provide an acknowledge bit if it determines that the message, the integrity of the message is good. So even if it doesn't need to use that information, this is something that it should do. So if I have several controllers on the bus, the more controllers I have on the bus, the amplitude of this acknowledge bit, assuming that the message was all received correctly, is going to be greater the more controllers I put on the bus, up to some point. I've seen this as high as maybe close to 4.5 volts and for the CAN high, and as low as something approaching half a volt or 0.5 volts. Those are probably about the limits you would see on that on a bus that is working correctly. Okay, let's take a look at Circuit Lab and try to figure out what's going on and why this occurs for. So what I have here is a simulation where I have 6 controllers on the CAN bus. I have this controller is the transmitting controller. It's the one that's sending the message. I've also taken the termination, I've divided it up into 2 terminators. Any place where it says CAN high and CAN low, these nodes are common anywhere throughout. That prevents me from having to draw wires to try to connect all those together, which would get really ugly if I tried to do that on this schematic. Okay, so the way the time domain simulation is going to work, I have these switches of the transmitting controller. You can see they're in the normally closed. I've got them set as normally closed. These switches are going to open after 2 microseconds. So we'll have 2 microseconds where we're trying to transmit that last bit of the cyclic redundancy check, assuming it's a dominant bit. And then we have 2 microseconds of the delimiter for the acknowledge bit. That's that period of time before. After that, at 4 microseconds then into the simulation, all of these other switches are going to close to simulate an acknowledge bit. So I have 5 controllers the switch will close. The transmitting controller has to listen during the acknowledge bit period. So when the acknowledge bit is being transmitted by the other controllers, the controller which transmitted the message, which is being judged or being weighed by the other controllers, the transmitting controller has to listen to see if the other controllers are okay with the message. So this is one rare instance in J1939 and CAN where more than one controller is going to transmit at the same time. The other being, of course, whenever arbitration. If several controllers, the bus is idle and start transmitting at the same time, it's a similar phenomena. So I'll go ahead and run the simulation. We'll go ahead and run it. And what we have here is this is the transmitting controller. This is where it's transmitting that last bit of the cyclic redundancy check, assuming that it's a dominant bit. And then we go to the Acknowledge Delimiter. This is 2 microseconds where everybody is in the recessive state. Everyone should be in the recessive state during this period of time. That causes the current, as we can see down on this lower trace, to be 0 amps. One thing to notice is that the current, when only one controller is transmitting, we have a current value of 17.79 milliamps, 17.79 thousandths of an amp. When all of the controllers are transmitting, all the other controllers, the other 5, the current increases from 19.79 to 20.35 milliamps in this case. What that ends up resulting is we have a voltage increase. And let's take a look at where that's coming from. So if I look at this system, what I can see here is I have a terminating resistor. I've put an ammeter in series with it, which is what we do with an ammeter. I have a voltage or a voltmeter in parallel across of it, just so that we can kind of see it here. The voltage which we're going to see during the dominant bit is going to be the product of, it's something that comes from Ohm's law. It's the current times the resistance. So this is a simple, if we look at this as a simple circuit, I have 17.79 milliamps flowing through 120 ohms. If you put that into Ohm's law in a calculator, you're going to come out, in this case, with a voltage of 2.135 volts. Because the terminators are in parallel, and if we assume, that's assuming that there is, we've negated the wire resistance. There's no resistance in the wire. We're going to say these are perfect wires with no resistance, no impedance. We're going to have, in this case, because these are exactly the same value, these are resistors in the simulation which are exactly the same value. If these were a little different value, the currents would be different, but because they're identical, we have the same current that's flowing through this other 120 ohm resistor. So because these guys are in, these 2 terminators are in parallel with each other, the voltage that is dropped across the terminating resistors must be the same. Anywhere in a parallel circuit, the voltage dropped across parallel components must be identical, has to be identical. Otherwise, you have to have another place for the voltage to drop. And we're assuming no wire resistance, therefore, all of the voltage is dropped across our terminating resistors. So the reason that when there's one controller transmitting, there is whatever voltage, the 3.5 volts difference that we saw, or the can high voltage being 3.5 volts, the difference in voltage about 2.5 volts is because this current, because of the current and because of the terminating resistor. As we decrease current, or as we open these switches, we know from the simulation for sure that it has to run to 0. It has to drop to 0, correct? Whoops, wrong thing. Let's do time domain simulation. And so here's our periods. Here's one resistor or one controller transmitting 17.79 milliamps. Here's no controllers transmitting. Nobody's putting anything on the bus. We're in the recessive state. We have 0 amps of current flow because there's no current flowing in the circuit. Therefore, we have 0 volts dropped across the 0 volts dropped across the termination. So if we look during the recessive state, the voltage across both sides of the terminating resistor, if I measure that to ground, it's 2.5 volts. Therefore, there is no current flow. If there's no difference in voltage across the terminating resistor, there has to be no current flow. Ohm's law requires that. If I have 0 volts that are dropped across something, that means I have 0 current that's flowing through it. So we can see that here in the simulation. When all of the 5 devices are transmitting at the same time, then our current increases to 20.37 milliamps in this case. And if we look at each of these components, if I take some of these away, if I remove some of the controllers, let's just take 3 controllers off of the CAN bus, go back to build. So I'm going to take these 3 controllers and I'm going to delete them. Okay, so they're gone. And let's run the time domain simulation again, we can see previously this is where our current level was. And now I've dropped down, I've only got 2 controllers which are transmitting, which isn't much higher than when I just have 1. So here's 2 controllers transmitting the dominant bit. We can see that the difference in voltage has decreased. So this is the reason that you see this acknowledge bit be at a greater level or at a higher level than the other bits. So this is because there's multiple controllers at the same time transmitting this acknowledge bit that causes the current flow through the terminating resistors to increase, which Ohm's law requires the voltage drop to then increase across that resistor. So when you see this other spike, if you would, at the end of the message, don't be alarmed by that. That just indicates that it's working correctly. If you look at a bus where you only have very few devices or maybe one other device on the CAN bus, then what that's going to result in is that amplitude of this may be at the same or a little less or maybe a little more than the original controller which is transmitting the message. Next time we'll take a look at what happens if the acknowledge bit is missing. It's some of the errors that occur, and we'll look at that in the next episode.